Hello, everyone. We're the electric motor dynamometer team for the Smart Superway. First off, my name is Alexis Corres.
I'm Rosa Martinez.
I'm Brian,
I'm Kai.
So I think you've heard plenty about the Spartan Superway, so we will go over this pretty fast, but a lot of the bogies that they use, a lot of the motors that they use that drive the cars, have many different aspects of motors that need to be tested for different parameters. So this is a prototype that they have shown many times in different versions and iterations, but all of them have the same kind of types of motors to be tested. For example, the hub motors at the top are the hub motors, and then there's going to be a motor driving the door, and I think the wheelchair team has a latch that drives the seatbelt over, so all of them have to have different parameters that need to be tested and have different powers, different torques, different speeds that all need to be refined and to a T to be perfect. So our project objectives have three main ideas in mind with design, scalability, and user interface. The first design, we wanted to incorporate hub motors, DC motors, and three-phase electric motors within our dynamometer to incorporate all of them and to test all of them. For scalability, we wanted to be scalable up to larger motors and potentially smaller motors too. Both iterations have to be considered and have different aspects to have them consider for us. And for user interface, we have the coding aspect where they display all the values, the torque values, the speed values, and the power values. Those are the main 3 points that we want to tackle in our design. So these are our design specifications. Motor types, shown earlier, the hub and DC motors for the wheels that drive the bogie and all the motors that drive the inner components. Test motor limit, we had to limit it in some aspects, as I believe the lower the RPM, the more torque it has, and it goes down exponentially. So there is a lower limit that we had to impose. A higher limit, of course, because we don't want to be breaking all of our stuff in prototyping, but we had a scope that we had to stay within. And also 1/4 to 1 horsepower for the motors as well, for similar reasons. Manufacturing costs, that's basically our budget. We want to stay within around 150. We saved a lot of money in different aspects, especially in 3D printing and prototyping, and just sourcing things from around here really helped with keeping our costs down. Test results, we wanted to stay within about 5% full scale and keep all the results and power to be relatively close together in that aspect. Documentation, we wanted the people or anyone who picked up our design to be able to recreate it relatively easily. So we had design drawings, we have CAD files, we have a manual that we could give to them, and display values is, again, torque, speed, power, the main components of a dynamometer to be shown. So when tackling this project, we had several options like bases to choose from. But more research, the more obvious the answer became. But the first iteration that we got was a friction brake dynamometer. It's very rudimentary. It basically has a rotor that clamps down and then has torque measured with a weight and a measured length, and then another RPM on the rotor. But the thing about this is that it'd be wearing down very easily, obviously with the friction, and it wouldn't be able to handle high powered motors. The higher RPM, it'd be wearing even faster and faster, so it wouldn't fit with our scalability. The next one we kind of researched and thought about was the hydraulic dynamometer, which really quick is where you cycle water through a casing around a disc, and that the vortices shown here would slow the disc down, and you use that to measure the torque, and then you have an RPM sensor right at the rod here, and you use that. The thing about that is it is relatively low cost to make, but it is very high maintenance. Any leakage in any area would be incredibly difficult to fix. So we decided against that, and Alex will go into why we chose this specific design.
Thank you. So as Brian mentioned, we had several options for dynamometers, you know, a breakdown, friction brake, hydraulic, but we ultimately decided that an electric eddy current brake dynamometer would be the best choice for us due to its simplicity. Here was our first like quick, let's call it a render of an idea we had. It's a very simple mechanism. As you see, we chose electric motor dynamometer. Over here, this is the eddy current brake. And if I were to show you this video, it's a very simple mechanism. Basically, So basically what's happening is as we spin a disc or a rotor, we can induce eddy currents to slow down that disc. So in this video you can see the RPM over here is 850 RPM, right? And as I bring a magnet towards it, it drops. That's an induced eddy current caused by the magnet and the spinning rotor. And we want to incorporate this, or we want to use this design. And for our initial semester, our fall semester, we want to really like get into design. We want to create our own dynamometer by scratch by making these red electric magnets, as you see right there. And we made a final render of that last fall to the picture over here to my right. But ultimately, sorry, transitions. My bad. To save both time and resources, we chose to reuse an old lab dynamometer that we had here. Just go to video of it running.
Motor running.
And as we increase the voltage on the dynamometer, you can see that this one right here would break, and it'll produce a torque. In this case, it's 3.5 foot inches. Sorry. And our final spring design, which is you can see here in the front, it incorporated many aspects of our design goals. We have our RPM sensor, not hooked up right now, but we're capable of measuring RPM through two magnets over here. We have our stator torque arm right here that will measure our torque. And we're also able to, we also coupled it with a hub motor tester right here with its own gantry. So for our final design, the yellow cylinder is our dynamometer, and we made 2 separate frames to test all types of motors. So the frame to my right here is my hub motor tester. The frame to the left right here is our universal motor tester that's capable of testing like stepper motors, DC motors, 3-phase motors. And it's, one thing we have to do is just swap it out from here with each other, and it's interchangeable. It's pretty easy. It only takes 4 bolts, and it'll work like that. As you see, the final spring design allows testing motors with simple adjustments. As I mentioned earlier, it's just a really quick, simple swap whenever you want to test a DC motor or hub motor. Here's a little bit of our hub motor tester. I'm the one that designed this one, and I wanted to make it as a little bit easy and a little bit more, I really kept that scalability in mind. This gantry allows you to move it up and down. You could add these little forks in place to incorporate larger hub motors. These rollers right here are adjustable to really be able to test these larger hub motors. In this case, we're testing this little red motor that they used for the bogie here a while back.
Okay, and then as you can see off here to the side, this is our
DC motor testing rig. The way that this is scalable is that this platform moves up and down as well with this universal motor mount. And then, if you slide to the next slide, we also designed these couplers because we realized that the size of the rod we were using is 5 to 8 inches in diameter, and the size of the rods for all the different motors were different sizes. So the way that this is scalable is that these couplers are different sizes. This is the same, it stays the same. This over here is the size of this rod, and this over here is about 4 millimeters. So it'd be really easy to just 3D print different sizes of these, and so adjust it to whichever motor you're testing.
So to display all of our parameters, we decided to go with creating a data pipeline. We started off with, so we have our sensors that will collect data and send it through the ESP32 that will send it to MQTT, then Telegraph, then Influx, and Grafana. So our sensors, we have our load cell, and our load cell will will be placed right here where the brake arm is, and it will read in kilograms, and then in the code it will calculate a torque. And then the next sensor we have is our Hall effect sensor, and this sensor will be placed right around here where the magnet coupler is, and it will take RPM data. And the next sensor is our current sensor, and this is to read the current output of the motor that we will be testing. And then for our voltage sensor, I actually went with the voltage divider. I was able to program it to where it can read up to 60 volts, and that was done with the calculation, where R1 would be 10,000 ohms and R2 would be 191,000 ohms. And then, so all this data is being collected from the sensors, and it's getting sent to the ESP32, where, and then from there, the ESP32 is connected to MQTT, which is, MQTT is our broker. So MQTT will collect all this data information from the sensors, and it's just collecting it and formatting in a specific format. And then from there, we wanted it to be sent to Influx, but Influx doesn't really communicate with MQTT. You need a plugin, and that's where Telegraph comes in. And Telegraph takes all this information that's just kind of scattered, organizes it so it can be sent to Influx, and then Influx can read it in its own manner. But Influx is also a time series database. So all the information that's being sent from Telegraph to Influx is already organized, and then Influx just adds a timestamp to it, and that is accurate down to the nanosecond. And then from Influx, it's all the collected data gets sent to Grafana, and Grafana is where we will have our visualizations, our graphs, our charts, our pie charts, everything. And the graphical data is displaying torque, speed, and it would display power curves and efficiency. And it would be something like this, because unfortunately we did not get to finish this. But essentially it would be something like this, where we display current and power and volts and anything, pretty much Grafana is customizable to whatever you need. So kind of going back to these services, MQTT, Telegraph, Influx, and Grafana, all these services were downloaded and installed into our server, which we used the Raspberry Pi for our server. And everything was running, everything was good. I did get to connect MQTT to Telegraph. Telegraph was reading last night, and it was connected to Influx, and all I gotta do was connect it to Grafana, and then this morning I just kind of decided not to connect, so, but yeah, that's unfortunate.
Unfortunately, as Rosa stated, we didn't get to our testing phase this semester. But regardless of that, we're still very proud of what we did here, what we learned. We learned so much. I learned so much about design, 3D printing. Rosa, she learned a lot about a full stack development. We Ryan, Kiara, we all worked together. We really tried to get this done, and unfortunately, things just didn't work out this time. But that's besides the point. As for what? Oh, Kiara, sorry.
Okay. After this whole process, my team and I agreed that we would like to see future groups pick up where we left off by trying to make their own electromagnet, which we struggled with a few semesters ago. It was really hard to get enough power, and it was really time consuming and expensive. So that's one of the things we would like them to see. The other thing is that we would like them to test these motors that we acquired from different things such as vacuums, or I think even a dryer.
Yeah.
A dryer, just so that this structure over here can accommodate those big type chunky motors. And then another thing would be, instead of having to switch this out for that, we would like to see the future group try to have one structure to test both hub motors and DC motors, so you just change the motor. A little ambitious, but we'd like to see that in the future. And then this project has a large societal impact because without knowing how efficient and reliable these engines are, we won't be able to reduce our greenhouse gases and affect climate change in a positive way. But thank you for your time.
Any questions for the team?
Your comments just at the end, what was the hitch? What was you were testing this code and I didn't quite follow how it didn't quite get to the finish line.
Okay, so yesterday I was coming to a few problems, and the last thing I needed to do for Telegraph to grab this information from MQTT to be able to send it to Influx was to go into the configuration file and set up a specific line protocol.
Yeah.
Because originally MQTT was sending Telegraph just values, just numbers, and Telegraph was rejecting it because it wasn't in the specific format. And then so I got into the configuration file, I adjusted the format, and it was running. It was showing me that it was connected to my Influx account, it even showed my email and everything. And then this morning I was having issues with MQTT through the ESP32 code. It was connecting, disconnecting, connecting, disconnecting.
Oh, no.
Yeah, so, but I think if I would have had maybe 2 more days, I probably would have been able to.
Can you still get that done?
I think I can, yeah.
I'd like to see it in the final report. That'd be awesome. Yeah. That really matters, collecting the data,
Yeah.
getting to the finish line.
Okay, very good. Thank you very much.